All right, everybody, good morning. Um, let's get started. Remember, we finished chapter 10 last time, right? Where we were doing all that categorical data analysis, right? So remember all of those tests, but we started chapter 12 last class where we started talking about the correlation, right? Relationships between two quantitative variables. And so one of the things that can get confusing here is we've seen data sets that look sort of similar to the data that we'll be given here in this chapter here. For instance, when we looked at this example last time, we looked at the length and weight of a certain species of snakes. And so we have paired data in this example. However, if you notice the two columns of data that we have here, they're measured on different units, right? So this is the type of analysis we're going to do when we have paired quantitative data, but we're not interested in the differences of the paired data. We're interested in the relationship, right? And so that's where correlation comes into play. We talked about that last class. We talked about how we're going to use a graph called a scatter plot to kind of see the actual relationship between the variables. And then we can use words like, oh, there's a positive relationship between these two variables if, as I look at that scatter plot from left to right, the points tend to go up, right? Or we can use something like a negative relationship. So I don't have this written here, but we can do the opposite, right? So if I look at my scatter plot and from left to right, my points go downward, I'm going to say that there's a negative relationship, right? And so we introduced this term here, correlation, and this gives us a number that we can kind of look at to determine what type of linear relationship we're going to have between the two variables, right? So in general, a correlation between two variables just means that there's a relationship between the two variables, all right? But we're going to be interested in linear relationships because we're going to talk about linear regression. So it says two variables are linearly correlated if they have a linear relationship as evidenced graphically. So when we do that scatter plot, a line of best fit kind of fits the data. That's what we're going to be interested in, right? We're usually not interested in nonlinear relationships. It's harder to model things non-linearly. And so we're going to talk about the simplest type of model that we can create to relate two variables. That's the linear model. All right, so graphically, we can describe a linear relationship. There's also a statistical index that we can use to do that, and that is your correlation coefficient. The correlation coefficient is given by the variable lowercase r. All right, it measures the strength and the direction of that linear relationship. So there's two things that I'm getting out of this number. All right, strength and direction. Right? Well, the direction we kind of talked about when we were looking at the scatter plot. It's either going to be a positive or negative. So when we were looking at the graph and it went up from left to right, we call that a positive relationship. Well, when I calculate the correlation coefficient R, I'm going to see a positive value. All right? Or it may be negative, right? That means the direction of that linear relationship is negative. That means from when I was looking at the scatter plot, the points went down from left to right. Now this thing here about strength is related to how well do the points approximate a line. So are all the points on a line, an actual line, if we were to draw it on our scatter plot? Are they very close to the line? That means we're going to have a strong correlation. Or are they scattered really far from a line of best fit if we were to try to draw one? That would be a weak linear relationship. So this statistical index kind of can confirm some of the stuff that we see in the scatter plot, all right? Now, it's calculated using this formula here, which is a pretty long formula. But it's 1 over n minus 1 times the sum from I equals 1 to n. And so what we're going to do is we're going to go to every single point, right? Remember, we have paired data. So if we were to look in our data set, we're going to have an x variable and a y variable, right? And so the first individual will have the ordered pair x1, y1, the second individual x2, y2, so on and so forth, till we get to the last individual in our data set. So when I look at this formula and I see this x sub I, it's telling me go to the first individual, get their x coordinate, subtract the sample mean of your x values, and divide by the sample standard deviation of your x value, right? So we talked about this before. This x sub I is an observation in our data set. This is our sample mean. And this is our sample standard deviation. I'm going to abbreviate that with SD. Right? When we take an observation and subtract the mean and then divide that subtraction by the standard deviation, what did we call that before? Is it the chi-squared? Chi-squared takes observed count minus expected count squared divided by the expected count. Lydia, what do we call that? Observation minus mean divided by standard deviation. Aaron? Yateen? Emily? Hugh? A z-score, right? Remember when we were doing a normal distribution? We would subtract the mean divided by the standard deviation and go to that normal table to calculate probabilities. So this is just saying, give me a z-score for this first x coordinate. And then I have almost the same thing multiplied here, but I'm going to look at the y-coordinate of that pair, right? So all I'm doing here is getting z-scores and multiplying them, adding all of them up, and then dividing by n minus 1, right? This method of coming up with a correlation is called your Pearson product moment correlation coefficient. All right? That is the most commonly used correlation coefficient for quantitative data. Note there are several others depending on what type of data you have. All right? This is always going to be a number between -1 and +1. All right? It has to have some negatives because it has a direction to it. Right? It measures the strength and direction. So it's going to have negatives and positives. And it has a strength, right? So the closer it is to either 1 or -1, so like 0.9 or -0.9, the stronger the relationship. All right? And that means if I look at the graph, the scatter in that plot would be close to the line, right? The points won't be far from a line of best fit. They will be close to that line. The closer it is to 0, the weaker the relationship. And so, now, I'm going to say this right now, but usually if R is greater than like 0.7 or R is less than or equal to -0.7, we say that that's pretty much a strong linear relationship. You can kind of use that as a rule of thumb. All right. Now, you may get out of here and go to biology, and they're going to say a correlation of 0.8 or -0.8 is strong, right? So there's some argument in statistics about what is a strong linear relationship. This is probably the lowest number that people consider as a strong linear relationship. All right. And of course, if it's not strong, it's getting to the weak side of things. All right. If it equals 0, then we'll say that x and y are not linearly related. So I have some drawings down here, or some pictures, of several different correlation coefficients. All right. If you look at the ends of this top row here, these above are the values of r. Notice here, when r equals a positive 1 or r equals a negative 1, we have a perfect linear relationship, right? Because those points are all on a line. So this is a perfect linear relationship. And this one is perfect. All right. If you notice, when I decrease my correlation coefficient, I'm going to have more scatter away from the line, right? So even when I have a strong linear relationship, like this 0.8 right here, my points are not all on the line, right? Same thing happens for negative 0.8, right? So this is strong, and this is strong. One of them is in the positive direction. From left to right, you go up, and one of them is in the negative direction. So we can say strong positive and strong negative. Then I can get to some weaker positive and negative, right? So this one's weak in the positive direction. So they're still going upward from left to right. But notice here, there's a lot more scatter. And then the same thing happens for negative 0.4. Now notice the difference between this strong and this weak here. One of the things that I like to do when I'm trying to determine whether there's a strong or a weak linear relationship is basically if most of my points kind of fit within a thin oval, then I'm going to say that that's pretty much a strong linear relationship. But as I get weaker, that oval becomes more circular, right? So you see in this example here, we have more of a circle. It's not a perfect circle here, but that lets me know when I'm trying to look at a scatter plot to tell if I have a strong or a weak correlation, it's going to be a weaker correlation. And then this one here with the correlation coefficient is 0, we're going to say that this is a nonlinear relationship. All right? So you can kind of see how the strength kind of carries. Now, these are kind of easy to see, but when we can deal with real data, especially when you don't have as many points on that graph as what we have here, it can be sometimes extremely difficult to look at the graph and say, oh, this is a strong negative relationship, or this is a weak negative relationship, right? That's why the correlation coefficient kind of helps us out. I wanted to include these two values here because those are also perfect linear relationships, right? So one of the things that people tend to do is confuse the correlation coefficient with the slope, right? So I'm including this here. Don't confuse R with the slope. No matter how steep your line is, if all of your points lie on the line and there's a slant to your line, your correlation coefficient is going to be equal to 1 or negative 1, right? So this is equal to 1 and this is equal to 1, even though they're different slopes. All right. Now there is one line that we're going to deal with that can have the points can make a perfect line, but we're going to say that there's not a relationship between those two variables, and that is a horizontal line. So we don't consider there to be a relationship between the two variables if the relationship leads to a horizontal line. All right. Because as one of the variables increase, the other variable is not doing anything. It's staying constant. So that other variable is not changing at all, right? So we don't consider there to be a relationship between the two variables if the relationship leads to a horizontal line, or can be described by a horizontal line. All right? So we need a slanted relationship. And then the last little bit here, these last four graphs here, they have a correlation of 0 because they are nonlinear, right? So remember, R only measures linear relationships. So these variables may be correlated because we see a pattern in their scatter plots, but that pattern is not according to a straight line, right? And so we're going to get a correlation coefficient of 0. Or we should. So when we go and collect data, we can calculate R. R is a statistic, all right? It's about sample data. What we're really usually interested in is the population correlation, all right? And so R estimates the population correlation, which is denoted with the Greek letter rho. Almost looks like a P, but it's a rho. R-H-O. All right? So when we collect data and calculate R, it's about the sample, but we can do a hypothesis test and construct a confidence interval about the population correlation. So we can construct a confidence interval and we can do a hypothesis test. And the hypothesis test is always going to be that there is no correlation, right? So my null hypothesis will always be that rho equals 0. We assume that there is no linear relationship between the variables. We gather our sample data, and we can test the alternative hypothesis that rho does not equal 0, rho is greater than 0, or rho is less than 0. Either of those. All right. The code that we're going to use here is core.test. It's core for correlation. It's going to give us the confidence interval and the hypothesis test. And note, we can use the alternative equals option when we're doing these alternatives equal greater or less than here. All right, I don't have it here on the notes, but we can add that as a third option here once we have our two data sets entered. So we can test whether it equals 0, whether it's greater than 0 or less than 0, or if we want to know how big we should expect that correlation coefficient to be in the population, we can construct the confidence interval. And then we can say that, hey, we do have a strong linear relationship, or my linear relationship may be pretty weak. All right, based off of that confidence interval. So I'm going to go back to that same example, and you're going to see throughout this chapter, we're going to use the same example here. But we're going to calculate the correlation coefficient R, and we're going to use it to describe the strength and the direction of the association between the length and weight of snakes. So let's do the confidence interval, and at the same time, it's going to give us the results for our hypothesis test. And we're going to do that as well. So in order for us to test or to get our correlation coefficient R, I'm going to use the core.test function. Notice here, my x is length and my y is weight, right? Length is x, weight is y. All right. Now what I did here, in my notes here, I put weight first and length second. We might have an issue, right? Because x and y matter, right? When we put it on the xy plane, when we did that plot function, I always wanted x first and y second, right? Scatter plot, do the plot function. Well, when we do the core.test function, the order does not matter, all right? And this is one of the only times that the order does not matter, all right? So you just put your two data sets into RStudio. Remember, we entered our data last time. We did length equals, we did C, and we put our values in there, and then we had weight, and we put the weights in there. And then when you're ready to do your core.test, you just do core.test, and the order doesn't matter. So I'm going to go to RStudio Online, and I'll pick up where we left off last time. So here you see we have our length, we have our weight. We did this plot last time. There it is again. We don't need this for this example here. But if you were to look at that, would you say that, okay, well, we can see that this is pretty much a linear pattern, right? And our line of best fit may be what I'm kind of drawing here, right? Do you think that's going to be a strong or a weak linear relationship? Okay, the closer the points are to the line, the stronger. The further away they are from the line, the weaker we would say it is. Raise your hand if you say this is probably going to be strong. Yeah, right? Now, this is a very small data set, so it's kind of hard. It's going to be kind of hard to see. We can verify that it's strong by doing that core.test. So I'm going to do core.test, and I'm going to do like I did in the notes, put weight and then length. And then I'm going to click run. Now notice here, I'm given all of these results here. All right, if I want to know what the value of R is, it's right at the bottom here. So my R in this example is 0.9436756. I'm going to write this in our notes. So it's at the bottom of the chart. All right, so we have it here. So since that is positive, and you can see that that's 0.9, that's close to 1. And we just said if it's greater than or equal to 0.7, if it's positive, that's a strong linear relationship. So I'm going to say that there is a strong positive linear relationship between the length and weight of this species of snakes in the sample. That's evidenced by that correlation coefficient R there. Now, if I wanted to go further and do a hypothesis test, right? It says we're going to test the null hypothesis that rho equals 0 using alpha equals 0.05. So for my hypothesis test, I'm going to have rho equals 0. My alternative hypothesis, it doesn't say anything about directionality. And so I'm going to have rho not equal to 0. And I need my p-value to draw conclusions here. My p-value is given in that same output. So I'm going to go back to RStudio and get my p-value. All right, so my hypothesis test is here, right? Notice my alternative hypothesis. The true correlation is not equal to 0, right? My p-value is 0.0001. Right, we can kind of expect that, right? Because that R is 0.94, right? That's a lot of evidence against the null hypothesis. And so what I'm going to do is I'm going to write that p-value in my notes, and then we'll come back. Uh-oh. So my p-value is 0.30 and then a 1. And my alpha was 0.05. So since my p-value was less than or equal to alpha, we reject our null hypothesis. We've gathered enough evidence, right? So we're going to say there is sufficient evidence to conclude that the population correlation between length and weight is significantly different from 0. Okay? It's significantly different from 0. That's what the hypothesis test gives me. Now, since we did our alpha at 0.05, we're going to want a 95% confidence interval, right? And this is useful because what the hypothesis test just tells us how that it's going to be different from 0, right? But how different from 0 we should expect it in the population, that's going to come from your confidence interval. And so I'm going to go back to my RStudio code because it gives the confidence interval results too. So if I go back, notice here under the hypothesis test, we have the confidence interval. I'm going to round these to 3 places after the decimal. So I get 0.749 to 0.988. So 0.749 to 0.988. All right. So now I can do that. And I can say that we're 95% confident that the true population proportion, that is not right. The true population correlation between length and weight is between 0.749 and 0.988. Right? So we're pretty confident that we're going to have a strong linear relationship in our population, right? Because the smallest number in that confidence interval is approximately 0.749, which is a strong correlation. And it includes values upward to 0.988. All right? Now, if I were to just give you this confidence interval here, okay? and say, can you tell me the results of this hypothesis test? Are you going to reject a null or fail to reject a null, right? What are you going to look for inside that confidence interval or not to make a rejection decision? What number? Caroline, what did you say? 0, right? Because our null hypothesis here is 0, right? So if I look at my number line and put my confidence interval in there, on there, and I see that 0 is not in the bounds of that confidence interval, I'm going to reject my null, right? That is the case here. 0 is over here, 0.79 is here, 0.988 is there, right? That's evidence to reject the null. If 0 is within the bounds of your confidence interval, that means one of these numbers is going to be negative, the other is going to be positive. Then that's enough evidence to say I'm going to fail to reject my null hypothesis. So again, we can use confidence intervals here to draw conclusions about our hypothesis test. All right? But that's it with the correlation coefficient. Strength and direction of your linear relationship. All right? This is some other information. You don't necessarily have to write this down. But when we did the core.test function, I put weight first instead of length, where weight was y and length was x. It's because the correlation coefficient, the order doesn't matter, all right? The reason for that is if you go back and look at that formula, you're just multiplying the z-score for the x times the z-score for the y. And so when you multiply, they call that commutative property of multiplication, the order doesn't matter. All right, number 2, when testing the null hypothesis that rho equals 1, a significant correlation, which comes when we have a p-value less than or equal to alpha, does not mean that we have a strong or a perfect linear relationship. All it means is that it's different than 0. So your correlation coefficient in your population may be weak. All we're testing here is whether that correlation coefficient is different than 0. It could be weak. It could be strong. We don't know until we really get that confidence interval. Another thing that you may see in research, another error that some people end up writing, is rejecting the null hypothesis does not mean that X causes Y, right? So anytime you take a course and they're talking about correlation, you're probably going to hear this statement here that correlation does not imply causation, right? Just because X and Y are strongly linearly related, it does not mean that X causes a change in Y, all right? It just means that there's a relationship between them. The only way that we can say that X causes Y is for us to do a true experiment, like a randomized controlled trial or something like that. Correlation coefficients are usually used in observational studies where you're going out and you're not manipulating the environment, not giving individuals in your studies treatments. So never say that X causes Y. And then the last piece is your correlation coefficient is highly sensitive to outliers. All right? So if you ever plot your scatter plot and most of your data are strongly related, or it looks to be strongly related, but you have some extreme observation that's off the pattern, that single observation is going to have a lot of influence on the results of your correlation coefficient. So what you'll usually do in practice is you'll take that data set out, or that data point out, and calculate your correlation coefficient, because it's going to mislead some things. All right? So that is all with your correlation coefficient. Any questions? All right. So remember I said in this chapter, we're going to talk about correlation and regression, right? Regression is what we really want to get to. So the rest of the chapter is about linear regression. So whenever we know that we have a strong linear relationship, we're going to want to create the line of best fit. And by creating that line of best fit, we can use that line to make predictions in the future based off of the single data set. All right, but we need, this is the qualifier here, we need the two variables to have a strong linear association. Remember, association in statistics is the same thing as relationship. All right, we want to find the line that fits that data. In regression, we always regress y on x and end up with a line that looks something like this. All right. Now, if you've taken algebra before, which all of you have, you've probably talked about y equals mx plus b a lot in an algebra course, right? What do we call m for this equation of the line? Anybody remember that? Slope, right? What does slope mean? What were some terms you remember about slope? Rise over run. What else? How would you calculate the slope? I remember, might have been a long time ago. Y2 minus Y1 over X2 minus X1, right? So you're subtracting your Y values. I'm just going to say it's a change in Y, that's a delta for change, over a change in X, right? You want to remember that stuff because we want to interpret your slope, right? And so notice it's something about your Y values divided by something with your X values, right? So when I try to get the units of your slope, I'm always going to get the units of Y divided by the units of X every single time. All right? Because when we interpret, we want to give the correct units. All right. What was the B in that formula from algebra? Y equals mx plus b. What was that b? Grace, you remember b? Your y-intercept. Y-intercept, right? So it's where your graph crosses the y-axis, where it intersects the y-axis. So whenever we create a regression line, we're going to use a similar equation. Of course, that's an algebraic formulation of that formula. We're just going to have the statistics formulation. It's just y hat equals b sub 0 plus b sub 1 times x. All right. This is usually the equation that we rely on. The stuff with the capital X and Y is like a generalization. All right. That y hat is called your predicted y value. So whenever you create a regression line, you're creating predictions, right? So y hat is your prediction when x is a certain value in your data set. B sub 0, notice it's kind of the opposite ordering from where we use y equals mx plus b. B sub 0 is by itself, so that's your y-intercept, right? It's the value of y when x equals 0. So the units of that would be the units of y, whatever your y variable is, all right? But your y-intercept is the value of y when x equals 0. All right, your slope is b1. It's a measure of the change in y when x increases by 1. Okay. And then the values for B0 and B1 yield what we call the least squares regression line. All right. What we want to talk about now is what do we mean by this least squares stuff? Right? This least squares regression line. All right, this is a method that produces this regression line. Well, in order for us to figure that out, we need to define some more terms, 2 more terms. One of them is a residual. A residual is associated with every single point, right? So remember, we have paired data, right? Each individual is going to have an X and a Y observation, right? So for every observation, there's a residual, and it's basically a subtraction of the Y values, right? Your observed Y value minus your predicted Y value. And it's a residual. Even though it's a residual, we use the variable E as its notation. So every residual is the difference between your observed minus your predicted. Okay? So just to visually see a residual, I have this scatter plot here. Of course, we're going to have an X variable and a Y variable. So this is my X-axis here. This is my Y-axis here. My regression line is always Y hat. So every single point on my regression line is Y hat. An X and a Y hat. So if I go to a point, I'm just going to choose a random point here. I'm going to do this point right here. This point is going to have an X coordinate and a Y coordinate. It's the first point I'm choosing, so I'm going to put a subscript 1. All right, for me to see the residual, I'm going to create a vertical line from that point to my regression line. Okay, I'm just going to... And this point is on the regression line, right? Notice that was a perfectly vertical line, or it should be. And so it has the same X coordinate. So I'm going to say that this is X sub 1. But since it's on the line, it's a predicted value. So that's a Y1 with a hat on top of it. And so when I say something about a residual, well, this distance from here to here, my first residual will be Y1 minus Y1 hat. So that vertical distance represents a residual. Notice that's going to be a positive value because the point is above the above the regression line. I can choose another point. For instance, let's go to this point right here. I'm going to call this one X sub 2, Y sub 2. I'm going to do a vertical line so that it can have the same X value. But now, since that point is on the regression line, that's Y2 hat, right? And so the difference between these two, I'm going to do Y2 minus Y2 hat. That is what I'm calling my residual. So this difference here is my second residual. Now this time, my residual is going to be negative because that point is below the line. So some of my residuals are going to be positive, others are going to be negative, right? But this helps me get to what I'm calling the least squares regression line. What I can do is I could create what we call our residual sum of squares. All right? Your residual sum of squares is just going to every single point and calculating its residual and squaring that thing. The notation for your residual sum of squares, remember where we're dealing with sum of squares between and within with ANOVA? This is that same concept here. But this is about the residuals. So sum of squares resid equals the sum from I equals 1 to n, there's n points, y sub I minus y sub I hat squared. So I subtract, square it, I'm going to get my residuals. So this is nothing more is the sum from I equals 1 to n, e sub I squared. All right, we're squaring them so that we can always get a positive value because some of the residuals are positive, some of them are negative. If we don't square them, when we do that sum without squaring, it's going to equal 0. And so the least squares criterion is going to choose the line with a slope of B1 and a y-intercept of B0 so that that residual sum of squares is minimized. All right? So we're saying that the line of best fit is the best straight line. It's the one that minimizes your residual sum of squares. So I'm going to take this thing right here, and I'm going to minimize it. All right? I've got to pick. Now, notice this y1 hat. We can replace it with its equation, b0 plus b1 times x. And this statement here, the residual sum of squares, looks like this here. All right? So I just replaced this, that y1 hat above, with this. This is the same thing as y sub I hat. So we'll choose betas B0 and B1 that minimizes this thing right here. Now, if you've ever taken calculus, right, you can find a minimum by, taking the derivative, right? And it just so happens that you can actually do this and come up with formulas for B sub 0 and B sub 1. Now, we're not going to use these formulas. We're going to use RStudio to help us get our stuff. But B1, this is the actual formula for B1. And this is the actual formula for B0. All right? That creates a minimum for our residual sum of squares. If B0 and B1 are these two things here. Again, we're not going to use the formulas. If you look in the textbook, there are some problems where you'll use this. One interesting thing here, you may wonder, well, why is, some people confuse the correlation coefficient with the slope? Well, notice my slope is nothing more than my correlation coefficient times, this is the standard deviation of y, divided by the standard deviation of your x variable, all right? So it's going to have the exact same sign as your slope. So the slope and the correlation coefficient are going to have the same sign, but there will be different values. All right? We're going to use the linear model function in RStudio to help us get this. This is important. Order matters. So when I use my linear model function, whatever I call my y data set, it has to go first. I'm going to use the tilde symbol, and then whatever I call my x variable goes second. Never switch this. It's not like correlation, all right? X and y matter once we get to regression. So I'm going to use this function, and then we're going to have to take a summary. We used this when we did the ANOVA function because RStudio doesn't automatically give us the results that we need. So we're going to have to use our summary function to get the output. All right? All right. So we're going to stop here today. Next class, we'll continue and try to get as far as we can with the rest of this chapter. All right? Homework 10 is on this stuff and odds ratio, right? So you may not be able to finish homework 10 just yet.
Is chapter 12 and 10?
It's 10.9 in chapter 12. Okay? So homework 10 is open, but we only scratched the surface on this regression stuff. So you may not be able to finish unless you work ahead. All right, that's all for today. Have a great day. See you Wednesday.